Okay, about the theory and of core collapse supernovae. So what we are interested in is the phase that we have before the explosion, where we have the proton-neutron star phase, where it's after the bounce. So we are left in the interior with a proton-neutron star, and then the stall has already is stalled now, a few hundred kilometers away from the star. And then here we still have asymmetric infall from the outer layers of the star. And we have a few really important processes like convection and SASI, which we're really interested for asteroseismology. So this is basically how you could picture this. And I think that this picture was also shown today with the proton-neutron star that we have in the center and the shock around it. So this lasts about 0.1 to 1 seconds. And then due to the accretion of the infalling matter, the proton-neutron star is going to grow in mass, but at the same time, it's shrinking down in radius and is cooling down via the neutrino emission, as we've already heard today. So here we want to study convection and SASI because these are the ones that are going to excite the proton-neutron star normal modes, and we're really interested in them because it's the main mechanism of gravitational wave emission. Now, there are people that are going to show much nicer results of simulations, but we already know that the simulations give us a strain like this, which is really highly stochastic. But then once we get a spectrogram out of this, we see that we have some characteristic figures. So that means that there is something that we can do. And this is performing asteroseismology. And then later this week, Alex is going to present an overview about asteroseismology. But basically what is being done is that we are solving the equations that describe the system. We get the frequencies and then we plot them on top of the spectrogram. So here you can see that we can really get some information about the system because we have pretty good maths. Now, from this picture, probably someone would say, okay, it seems that the job is done. All the modes are more or less classified with some accuracy. But as we all know, this is not the whole picture because we also have SASI, which is the standing accretion shock instability. So this is the characteristic oscillation frequency of the shock. And we expect to have it like below 200 hertz. So this is something that we want really to capture. So how are we going to do that? So the steps of asteroseismology, they have already been described also by Daniel Murphy today about the Newtonian analysis. So I'm going to just give you a bit quickly the steps. So we're using general relativistic hydrodynamic equations, and then we perform a linear perturbation analysis around an equilibrium star, which is in hydrogen equilibrium, but is not static anymore. Now, these equations are going to form a generalized eigenvalue problem, and in order to solve these ones, we need to use the data from core collapse supernovae simulations. Once we obtain the solutions, then there is the tricky part of classifying the modes and inferring properties of the star through universal relations. Now, about the two last, there have been already some mentions, and there will be even more. So today, I'm going to focus on how to solve the eigenvalue problem and the methods we have proposed. So as I said, we can have the system of equations in the form of a generalized eigenvalue problem, where A and B are the coefficient matrices, while eta is the matrix of the perturbations, and sigma are the wanted eigenfrequencies. Now, by having this and getting the correct boundary conditions at the shock, which we are using Rankine-Hugoniot conditions, then we can solve the system. Now, I'm not sure if it's very visible, but the two methods that we are using to solve this system is the spectral methods, and then we also tried a machine learning technique based on physics-informed neural networks. So the first one, spectral methods, I will go quickly, but if someone is interested in any of the methods and more technical details, we can talk more. So we use a Chebyshev collocation method, and by building now the differentiation matrix, we can have the equations written in a discretized form. Why we chose spectral methods is because of some of the advantages they have. They converge exponential, and this is something I'm also going to show you. And that means that now we can have smaller grids in order to solve our problem, and it's much faster. And I already mentioned that we can have all the equations written in a discretized form, and then we can get at once all the frequencies, including complex frequencies. So we do not need to have any shooting method or having loops of iterations in order to find all of them. And then another feature that is really important is that regularity is imposed by definition. So now we have the new system of equations that has now also the accretion shock and also has the advection. And now we have also a new method, the spectral methods. So we want to check what's going to happen if this system works. So we consider 3 different cases of study. The thing that you cannot see up here, it says that is L equal to, because this is the one we're interested for gravitational waves. So in the first case, we are going to have an ideal setup in order to get P and G modes in a sphere. And here we consider ideal fluid where the sound speed and the adiabatic index are constant, while for this case, the velocity, the effect velocity, is still 0. So what we do basically is that we do an ansatz of the buoyant region. So by varying the Brun-Vassala frequency, we can have a region that there is no buoyancy and a region that there is. Now, once we check this, then we want to go and move on to include also the velocity, which is the main thing we want to have. But we want to have an analytical test, and this one was provided by the plane waves in a one-dimensional flow. Now, once we do this, then we consider accretion flow in a fluid sphere, where we assume that the Brun-Vassala frequency is 0, and then for simplicity, we have some of the fluid variables constant, while we have a general lapse and the velocity is 0 as it's smaller than 0 as it is subsonic. So let's start with the first one, with the P and the G modes in a sphere. So we consider 3 different models, 2 neutron stars and a white dwarf. And the results we get are here. So these are the frequencies with respect to the value of the Brun-Vassala frequency. So here we can see that it's characteristic that we have 2 different modes, 2 different families of modes. And this line here, the black one, is actually the Brun-Vassala frequency. And you can see that all modes underneath, they are actually parallel to this one. Therefore, these are G modes. While up here, we have P modes, and there are some constant lines, and these are the solutions that we have for n squared equals 0. When the Brun-Vassala frequency is 0, we know that the system has analytical solutions, and we put them with constant lines. So we can see that as we start with low values of the Brun-Vassala frequency, we follow these lines, while when we get to higher values, then we see that they deviate more and more. So what happens in this region here is the avoided crossings that you already heard about. So we have the interaction of the modes. And now here, the 2 neutron stars have more or less the same behavior, while the white dwarf behaves a bit differently. And we think that this is due to relativistic effects. Now, the same behavior that we can see for the frequencies, we can also see that for the eigenfunctions. So we see on the upper plots 2 P modes and the lower one 2 G modes. And in all of them, we start by increasing the Brun-Vassala frequency. First, the amplitude starts changing. But as we go closer and closer to the avoided crossings, then we also have the deformation of the eigenfunction. So now, as I mentioned, when we have 0 Brun-Vassala frequency, we have analytical solutions. Therefore, we can have a convergence test. And what I show you here is on the upper plot, the error that we have in the frequency, while in the lower one, the error that we have in the eigenfunctions. And you can see that we do see that we have exponential convergence. And here, the error is growing again with the total number of points. And this is also characteristic of the spectral methods because the accuracy depends on the condition number of the matrix. Now, the upper lines here that you can see in both plots, they are the convergence that we got from the code that has been used in the Valenthian group, great. And you can see that it doesn't perform that great in this case. I mean, we have quadratic order convergence, while with the spectral methods, we can have exponential. So now we move on to the plane waves case, where here we consider that we have one-dimensional flow. And this is the only analysis from what I'm going to show that is Newtonian, because the relativistic one was too complicated to have analytical solutions. So we have here the exterior, and we have our accretion shock here. And here we impose the boundary condition that the perturbation of the velocity has to be 0. Therefore, our perturbations now live here in this space where we're going to solve our equations for constant fluid variables and constant velocity. Now, by doing this, we're going to get the following results. So in the left plot, I have the real part of the frequency with respect to the velocity, and the pink constant lines, they are the analytical values, while the little blue stars, they are the ones we obtain numerically. So you can see that we have a perfect agreement, and you can also see that we have basically P modes with decreasing frequency. But now what is really interesting here is now we also have an imaginary part, and this is the effect that we have of the advection. So in this case, we have negative imaginary part, and therefore we have stable modes. But in real cases, we expect also to have positive imaginary part and unstable modes, and we expect to see SASI in that region. So now after this, we consider now the third case where we're going to have a fluid sphere with accretion flow. In that case, we get the results and we see that we have 3 different categories of modes. I'm not calling them families because this is just an ideal setup, so we're not sure which of them are an artifact of the approximations we made and which ones we should really have in realistic cases. The first one is the stable branch, where we have basically, again, P modes with decreasing frequency, and they resemble a bit the case of the plane waves, while you can see that the imaginary part is always negative, and therefore we call them stable for that reason. Now, on the other hand, we have 2 different branches of unstable modes. We consider that they are 2 different branches because you can see, so the colors here are the different values of the velocity that we are using. And you can see here that these frequencies look like they belong to a continuum. And in this region, the imaginary part is bigger than the real part, but the real part is still significant. While in the region over here, they look more scattered, and the real part is basically just an error, while the imaginary part is evident. So this region looks like we have purely imaginary modes. Now, so these results have been obtained by having some approximations, for example, the profile of the velocity that we're using. So we know that in the realistic cases, we will have imaginary modes, but we do not know if they're going to be purely imaginary or if we will have a case like here that the real part is still also significant. So this is something that we are actually studying now. So now the other thing I want to show you is the other method that we use to solve the problem. So we implemented the physics-informed neural networks, and basically here we have a neural network that now also incorporates in physics information, as now the loss is the residual of the PDEs that we want to solve. So again, if someone wants more technical information, I'm free to discuss, and I will just go quickly. We have 1 input node, and then we have 2 layers of 256 neurons each, and then we impose our boundary conditions through the form of hard enforcement. Now, in this case, we consider now the case that we have the Brun vessel frequency 0, and we actually have a static sphere of radius, unity, density, and sound speed for simplicity. So we chose this test because it has analytical solutions again. So here what we did is that we got 1 pin to do a search into the frequency domain. And we knew that we have to satisfy this boundary condition, which means that this perturbation would be 0 at the outer boundary. Therefore, every time that we cross this line, we know that there is a solution there. Therefore, what this pin does is that it checks when the sign changes, and then it identifies that there is an interval containing a solution. So except from this information from this plot, we can also see the importance of the loss, and we can see that when we used a high value of the loss, then we could not get the intervals right, or we could not get them at all. So once we find these intervals, then what do? Then we have two different methods in order to actually compute the eigenvalues, our frequencies. Now, we did that with a bisection method, which used as the eigenvalue solver the pin that actually was searching for the frequencies. And we did it also with another way by having a second pin, which now is going to have the frequency as a parameter. So both of them have advantages and disadvantages. The bisection is much faster because we use, in principle, a pre-trained network, while the other network is much more accurate. And here I'm showing you just some results that we got for a higher order mode. And you can see again the importance of the loss in these modes. So we managed to get this test case, but then since we saw that this method was much slower than the spectral methods, we are focusing more on the spectral methods for the moment, but we have opened this topic for some suggestions to improve it. And by this, I'm going to conclude. So as a takeaway message, which I think is a takeaway message from many talks, is that asteroseismology is really important in core collapse supernovae, because this is a way that we could actually infer properties of the proton-neutron star in the case that we have gravitational wave detections. And then our contribution to this is that we included for the first time the accretion flow and the standing accretion shock. And we introduced two different eigenvalues solvers, one with spectral methods and one with the pins. So we are working currently on incorporating the data from core collapse supernova simulations, and we hope we capture the SASI. And then as something that we can do in the future is that we can consider the non-calling approximation, because now we have all the space-time perturbations equal to 0. And then another extension of our method could be to binary neutron stars, and this is another project that we have. So by this, thank you for your attention.
All right, thank you. Thank you very much, Dimitra, for the great talk. Any questions? I think we have time for maybe one or two. We've got two at the back, so I'm gonna come and pass you the mic. You can start with this one.
Thank you for this wonderful talk. So regarding the pins implementation, I was very much interested to know how did you compute the loss function? That's my first question. And for the second part, when you were talking about the frequency, did you include curriculum learning in that pins?
No. For the second question, no, we did not include. For the first, the loss is actually the residual of the PDs that we're using. Then if you want, I can show you specifically how we got, what's the exact relation that we have.
So you didn't include the MSEs or just the loss functions from the PDs?
No, we get the mean square error of the PDs. We get a combination of those two.
Okay, yeah, thank you very much.
I'm sorry, while she's asking her question, can Alejandro get ready for the next talk, please? Thank you.
Okay. Thank you for the talk, by the way. Something I was curious about when you were mentioning including the SASI in the modal analysis for the first time. How would the accretion flows from there? Do you think they would affect the G modes, the P modes, or the F mode more, or are they completely, or do they create entirely new modes?
Well, no, we think that it should have an influence, because we already see from the analysis that we had for example, for the plane waves, we already have an imaginary part. And the studies that have been done up to now, the frequencies, they are only real. So we should, at least we should see that we have complex frequencies. for sure. And then this is what we want to see, how the modes will actually change, including this, because up to now, from what I know, advection has not been included. And so we want to see what corrections we will have. And also we want to capture then SASI.
All right. I think we